Today we will learn about Lewis structures in covalent compounds. A diagram that depicts valence electrons as dots and shared electrons as lines around the atomic symbol is called a Lewis structure. In the example below, you have two nitrogen atoms bonded together. As you can see, there is a pair of valence electrons, or a pair of dots, on each of the two nitrogens. There are also three lines connecting the nitrogens, meaning that the two nitrogens share three pairs of electrons. Looking at the other structure, you see there's a carbon in the middle and it has four lines leading out of it. Each line leads to a different hydrogen. So that means carbon has four pairs of shared electrons. Each pair is shared with a different hydrogen. So we already know that nonmetals are looking to get 8 electrons, but when they're bonded to other nonmetals, they have to share the electrons. So now let's see what that might look like by looking at Cl2, or two chlorine atoms bonded together. Notice how both chlorines have 7 valence electrons. They have 7 dots each. Now, both of these chlorines are looking to have a full octet. Remember that octet rule? They want 8 electrons in their valence shell. Well, that means that each chlorine needs to get one more electron. In this case, they're going to share their 7th electron, the lone electron, with the other. These two lone electrons get together to make a single shared pair. That means that we're going to take those electrons and replace them with a line representing a single bond. Now let's look at another example. Let's look at two oxygen atoms bonded together. Now both oxygens have 6 valence electrons. In order to get a full octet, they will need 2 more electrons each, which means they're each going to have to share 2 pairs of electrons. So let's do that. We're going to replace 1 electron on each with a single bond line. And then we're going to take the other lone electron from each oxygen and combine them to make another shared pair. Since we have 2 bonds between the same 2 atoms, we call that a double bond. So single bond is 1 line between the atoms, double bond is 2. Now, you might be asking, can we have 3 bonds? Well, yeah, you can. You can have a triple bond where 3 pairs of electrons are shared between the same 2 atoms. So that means each atom's going to have to contribute 3 different electrons to the sharing. Nitrogen gas is a good example of this. So far, we've only been looking at the situation where 2 atoms are bonded together to form a molecule. However, atoms can bond to more than 1 atom at a time in order to make larger molecules. The important thing here is to always make sure the valence shell is full. So your atoms all need 8 valence electrons except hydrogen and helium, which only require 2. Remember that duet rule? Now, in this example, we have 4 different hydrogen atoms, and each hydrogen atom only has 1 electron. It wants 2 electrons to fill up that s orbital. So hydrogen's going to have to contribute 1 electron to a shared pair. Carbon, on the other hand, has 4 valence electrons, and it follows the normal octet rule. So it wants 8 electrons. It needs to share 4 of its electrons with other atoms. This is why when we drew our Lewis dot diagrams, we draw one on each side so single electrons in 4 different orbitals before we went back and added the second electrons, so the pairs, because if we had 2 pairs and 2 empty spaces, there would be nothing to share. Anyhow, so the carbon is going to share one of its electrons with each hydrogen, and so each hydrogen carbon is going to have a single bond. And if you count the bonds, each hydrogen has one line or one pair it's using, so that duet rule is satisfied, and the carbon has 4 lines or 4 pairs, which is 8 electrons. The octet rule is satisfied. We are good. Now let's look at different types of covalent bonds. So if you have one line, then that is made up of 2 electrons, one from each atom, and we call that a single bond. If you have 2 lines, you have 2 pairs of electrons being shared, or 4 electrons total. We call that a double bond. If you have 3 lines or 3 pairs shared, you have 6 electrons total to make a triple bond. So, how do you draw a Lewis structure? Well, first you need to determine the number of valence electrons for each atom. So, an easy way to do this is to look at your periodic table. If you look at the groups, they tell you how many valence electrons they have, with the notable exception being helium, since it only has 2. Just make sure for groups 13 through 18, you only use the numbers 3 through 8. You do not have more than 8 valence electrons. Step 2 is to draw all the valence electrons around the element symbol. So you want to draw your Lewis dot structure for each atom. Make sure you draw each as a lone electron before you start pairing them up. So you want 4 lone electrons before you start pairing. Step 3 is to figure out how many times each atom will need to bond in order to get a full valence shell. Remember the duet rule and octet rule. Speaking of which, watch out for small atoms like hydrogen that only want 2 valence electrons. Next, you need to remember each atom will share one with another atom if they're willing to share back. So, a pair of electrons is shared when each of the 2 atoms contributes 1 electron. You're going to take those bonded electrons and draw a line for the bond. Do not draw the dots for those electrons anymore. So here's a few tips. Lewis structures show how electrons are shared amongst atoms. They do not show what the molecule would look like in 3D or in real life. Because of this, there are a few tricks you should consider doing when drawing Lewis structures. Even if they seem silly now, they'll make your life easier when we get to other topics. First, try drawing water and its cousins, so similar molecules like H2S and H2SE, at right angles. This will make them look closer to their actual real-world geometry, and it will help you when we discuss molecular geometry and polarity later. Make sure you draw carbon dioxide in a straight line because double bonds do not bend. Once again, double bonds do not bend. Usually, the atom with the lower electronegativity goes in the middle. So if you look at your electronegativity chart, you'll see oxygen has an electronegativity of 3.4. It attracts electrons. The lower electronegativity is going to be in the middle, the 2.64. for carbon. When one atom has multiple lone pairs, they go next to each other because the lone pairs take up a lot of space and make the molecule lopsided. That's why we draw H2O and similar molecules at a bend. Remember, negative areas with lots of electrons means they're going to repel other electrons. That's going to push the bonded pairs closer together. Now, pause the video and try the show what you know questions. Our first question is H2O. So, if we look at H2O, notice how you have two hydrogens and hydrogens can only form a single bond. So you know because of that they can't go in the middle. The oxygen, however, has 6 electrons. It has 2 lone pairs that are going to stick around, and then it has 2 lone electrons. So when the lone electron from oxygen hooks up with a lone electron from hydrogen, they share them to make a bond, and the oxygen must do that with 2 different hydrogens, and that's how we end up with this structure. Let's try CCl4. In this case, C has 4 valence electrons, so 4 lone electrons. They're not bonded or shared in any way yet. And chlorine has 7 valence electrons, which are made up of 3 pairs and 1 lone electron. So chlorine can form 1 bond with its lone electron. So we're going to put the chlorines on the outside, and each chlorine is going to bond to the carbon through one of carbon's lone electrons. And that makes 1 pair of shared electrons, or 1 bond between the carbon and each chlorine. Now let's look at Br2. Br, or bromine, has 7 valence electrons. 6 of them are made up of pairs of electrons, and 1 is alone, it's by itself. So that 1 lone electron can be used to bond. So the bromines are going to each contribute 1 electron to make a shared pair or a bond. Now let's look at example 4, HCl. So H follows the duet rule, which means it's 1 valence electron can be used to share a pair with another atom. Chlorine, on the other hand, has 7 valence electrons, so 6 pairs and 1 lone. In order to fill its octet rule, so have 8 electrons being used, it needs to share its lone electron. So the H and the Cl are going to share the pair to make a bond, and now hydrogen has 2 and chlorine has 8. Number 5 is C2H6. So, as we already know, hydrogen can only form 1 bond each, so we're going to have to bond our 2 carbons together. Now, each carbon has 3 more lone electrons that can be used to bond with hydrogens. Notice how each hydrogen is now complete duets, and each carbon now has a complete octet because each bond is 2 electrons. On example 6, we have H2S. So let's draw our S in the middle with our 2 H's at a right angle. The reason why we are putting the S in the middle is because H can only form a single bond. We know that sulfur has 6 valence electrons, so we're going to have 2 pairs of electrons and 2 electrons that are by themselves. These lone electrons can then combine with electrons from hydrogen to form a shared pair. So that shared pair is a bond between sulfur and hydrogen. Now notice how hydrogen has a complete duet, so that hydrogen is good. Sulfur has a complete octet, that one's good. And the other hydrogen has a complete duet, that one's good. Remember, each bond counts as 2 electrons. Let's try a few more problems. First, let's look at O2. Here we have 2 oxygens. Each oxygen has 6 valence electrons. Now, let's do our 2 pairs of electrons and our 2 lone electrons on each oxygen. These lone electrons are going to need to be shared with another atom in order to make a bond and complete the octet rule. In this case, oxygen has not 1 but 2 electrons, so 2 bonds it can form. There's only one other atom, so it must bond to the other oxygen. We make a double bond between the oxygens. Okay, so the oxygen has 4 electrons in the lone pairs and another 4 in the bonding pairs, and so each electron has a total of 8 electrons and completes the octet rule. Now let's look at number 8 in H3. So once again, each hydrogen only has 1 electron, so it can form 1 bond by sharing that electron. Nitrogen has 5 electrons. When you place these on your Lewis dot diagram, that's 1 lone pair and 3 unpaired electrons. So these unpaired electrons are each going to pair up with an electron from a hydrogen to make a shared pair of electrons, or a bond. Now, hydrogen has a duet completed, and so does the second hydrogen and the third. Nitrogen has two paired electrons up top, a lone pair, and then 2 electrons in each bond. So that's 6 bonded electrons for a total of 8 electrons, or a complete octet. Now let's look at 9, CO2. So we're going to place our C in the middle and the oxygen on the outside because we want our molecule to be as symmetrical as possible. So in this case, carbon has 4 unpaired valence electrons. Each oxygen has 6 valence electrons, which is 2 lone pairs and 2 unpaired electrons that can be used for bonding. Now, in this case, we're going to draw a bond between each oxygen and the carbon. Notice how we still have 2 unpaired electrons on the carbon and 1 on each oxygen? Well, in that case, let's go ahead and pair the carbon and oxygen up one more time, make a double bond. Now, oxygen has a complete octet, so does carbon, and so does the other oxygen. Let's have a look at number 10, PCl3. So phosphorus is going to be our central atom, since it's the one that's different, and we're going to make it have 5 valence electrons. 2 of these will be in a lone pair, and the other 3 will be unpaired electrons for sharing. Each chlorine has 7 valence electrons, 6 of which are in pairs, and 1 is unpaired for sharing. So each chlorine can make a single bond to the phosphorus by sharing an electron from each of the 2 atoms. We now have 1, 2, 3, 4, 5, 6, plus 2 for the bond is 8 on chlorine. For phosphorus, we have 2 unbonded electrons and 6 bonded electrons from the 3 shared pairs for a total of 8. The other 2 chlorines also follow the octet rule, so we are good. Now let's look at number 11, HF, or hydrogen fluoride. Once again, hydrogen has 1 electron that it can bond with. Fluorine has 7 electrons, 6 of those are paired up, and 1 is used for bonding. So we bond the 2 together, hydrogen has a complete duet, fluorine has a complete octet, and we are good to go. Now let's look at number 12, sulfur dichloride. So sulfur with 2 chlorines. We're going to put the sulfur in the middle because each chlorine has 7 valence electrons. 6 of those are paired up and only 1 is unpaired for sharing. So that 1 unpaired electron is used to bond to the sulfur. Then same thing on the other chlorine, and now we have a total of 1, 2, 3, 4, 5, 6 plus 2 for the bond is 8 on chlorine, and 1, 2, 3, 4 plus 2 for this bond and 2 for that bond is 8 on sulfur. So sulfur has a complete octet, and so does the other chlorine. Now let's look at H2SE. Once again, hydrogen is never our central atom because it can only make 1 bond. So let's put the Se in the middle, and Se has 6 valence electrons that form 2 pairs and then leave 2 unpaired electrons to be used for bonding. Now each hydrogen bonds to 1 of these unpaired electrons, forming a shared pair or a bond, and we are left with 4 bonded electrons and 4 unbonded electrons on the Se. Each H also has a complete duet thanks to the bonded shared pair, and we move on to number 14. For number 14, we have CH3Cl. Now in this case, we know hydrogen can only form 1 bond because it only has 1 unpaired valence electron. And we also know that chlorine can only form 1 bond because although it has 7 valence electrons, 6 of them are paired up. So there's only 1 unpaired electron that can be used for bonding. So we're going to put the carbon, which has 4 unpaired valence electrons, in the middle because that carbon can form 4 different bonds. Now the carbon is going to pair up with the chlorine for 1 bond, and the electron from the carbon will also go to a shared pair or bond with each of the 3 hydrogens. Now chlorine has 6 unbonded electrons and 2 bonded that are shared. Carbon has 4 bonds around it, which is 8 electrons. Hydrogen each has 1 bond, which is 2 electron. So carbon and chlorine each have a complete octet, and each hydrogen has a complete duet. Lastly, let's look at number 15, NF3, or nitrogen fluoride. Once again, fluorine, F, has 7 valence electrons. That's 3 pairs and 1 unpaired electron meant for bonding. And then nitrogen has 2 electrons that are paired up as a lone pair and 3 that are unpaired for bonding. So each fluorine can make 1 bond, but the nitrogen can make 3. So we're going to put the nitrogen in the middle and we're going to bond it once to each of the fluorines. Check to make sure you have complete octets, and we do indeed have complete octets for all 4 atoms. We are done.